Let's discuss some topics from network theory that we need to estimate poles and zeros in electrical networks. So what kind of network analysis do we have? Well, we have symbolic analysis, and the purpose of symbolic analysis is to find design equation. And we have numeric analysis, and the purpose is verification, find the answer. Is the circuit behaving according to our expectation? It's important that you have different types of analysis. We have in symbolic analysis, you can do it with slide cap. We have stationary linear instantaneous behavior and small random variations. We have dynamic behavior, and we have noise behavior modeled in possible in this slide cap. And numeric, you usually use SPICE or LT-SPICE, and there you have operating point information to find the linearized circuit, DC, stationary nonlinear instantaneous behavior, AC, stationary linear small signal dynamic behavior, and noise and transient, which transient solves the complete time variant nonlinear dynamic equations. So the basis of network theory that we use in those simulators is nodal analysis. And the nodal analysis uses Kirchhoff's current law. It says that the sum of the currents flowing into a node or flowing from a node equal 0. So here we can write the nodal equations for a network in the current equals some admittance matrix times the vector with nodal voltages. And the currents is then the sum of the currents flowing into the nodes. This is then the structure of a matrix, of the matrix, the admittance matrix. On the diagonal, we have the sum of admittances connected to a node, and off diagonal, we have minus the sum of the admittances connected between the node, two nodes, of which the indexes are those of the matrix element. Let's see, if we do this, if we do the nodal analysis, you see we have to write the elements in voltage controlled notation. So the current is a function of the voltage. This is not always possible. A voltage source does not have a current depending on the voltage. No, it has a voltage that is always the same for any current. So it is a current controlled notation. In order to deal with those elements, you could do network transformations, Theven and Norton, or we can modify the nodal analysis and bring an extra element in it and call it then modified nodal analysis. And here you see an example in which we have a voltage source, and we assume that through the voltage source there is an unknown current I through the voltage source, and we add it to the vector of nodal voltages, which is the vector of unknowns. And then, of course, we also need an extra equation, and the extra equation that we have is that the voltage node G minus the voltage node K equals this voltage. And you can see this is the last equation in the branch equation in the matrix. And this is how we deal with those elements. In this way, we can have a very compact description of a network, and this modified nodal analysis is the basis for both SLICAP and SPICE simulators. Now let's look, if you want to have a transfer function from one independent variable to a dependent variable, then you can calculate it in this way. It is the ratio of two determinants. One is of course, the denominator is the characteristic equation, and the numerator is a determinant of a minor matrix. And the poles and zeros can thus be found for such a transfer function by having either the numerator set to 0 or the denominator set to 0. So here you have the relation between what we discussed before, poles and zeros and the mathematics, and the network theory. Now let's dive a little bit more into this. So the time constant matrix is a matrix that we are going to use for determination of poles and, well, poles, but you can also use it for zeros in networks without feedback. So let's look at this modified nodal analysis matrix, this M. We say M equals G plus SC if we have first order differential equations only. So it has a instantaneous part and it has a, you could call it, dynamic part. And the characteristic equation was the determinant of M equals 0, which then can be written as the determinant of G plus SC equals 0. And here we recognize the generalized eigenvalue problem. If you multiply both, if you multiply M with the inverse of G, then you would find the determinant of the identity matrix times lambda or S times something which is a time constant, because it is 1 over G times C, which is RC. And we call it the time constant matrix. Now, if tau is an eigenvalue of the time constant matrix, then we have a pole at -1 over tau. This is the definition of how you find poles from this matrix. Are we going to calculate it like this? No, but this gives us the basic for doing estimation later on. This resistance matrix, this R matrix, we can find it in a way. This is described in the book in a mathematical way, but you can also find it just from circuit inspection. And what we do is we take all of the elements, the reactive elements, out of the circuit, and we make a resistive multiport element. And in the left picture you see I have a multiport to which capacitors and inductors are connected. And then I'm going to define the transfer function from voltage to current or current to voltage for all these ports. Let's say a capacitor I replace with a current source, and I measure at that port, as you see for C1, I replace it with I1, I measure the voltage V1, and then I have to transfer from a port current to a port voltage, and the dimension, of course, is resistance. Basically, this is the resistance seen by the capacitor. But it can be such that this current also causes a current through, well, let's say it cannot change the current from an open circuit, so through a voltage source, and that is done by, sorry, that replaces an inductor. You see the L, the self-inductance L, so L1, we have replaced with a voltage source, Vp plus 1. And the current through this voltage source can be caused by the current that we put in this capacitor port, and that means there will be interaction between the voltage or current flowing from the capacitor into the inductor, so the voltage across the capacitor, and the current through the inductor. But if you look only to the voltage source itself, there will be, if we change the voltage, there will be also a transfer to the current in that port, and which is then the resistance seen, or better say the admittance seen by the inductor. So in this way, we can demonstrate the application of this for, here we have an oscilloscope probe circuit. On the left you see the probe, on the right you see the equivalent circuit of the oscilloscope probe. This is a voltage source on the left with a 50 ohm, and then we have the capacitive and resistive attenuator of the probe. Now let's estimate or calculate the poles and the zeros of this circuit using the eigenvalues of the time constant matrix. Then we need to build this multi-port circuit that is here. You have 50 ohm, 9 mega ohm and 1 mega ohm. We multiply this R matrix. You can calculate the R matrix here. That's here, that is done. And then you multiply it with the C matrix, which has only the capacitance on the diagonal. And then the eigenvalue of the result of this RC matrix are the poles of the circuit, as you see it here. Now let's dive, because basically what we are going to do, we want to go to intuitive estimation of the poles and zeros of a circuit, which means we are not going to calculate eigenvalues. We want to, but this method is the basis for this intuitive estimation. That's why I need to introduce this first.